Thank you, Joe, for the nice introduction. I appreciate it. And a pleasure to be here. Hello, everyone. My name is Anniek. I am co-founder of Overstory, and I'm calling in from Amsterdam today. I will first shortly introduce myself and my co-founder Indra. So my background is in business and psychology, and I'm co-founder of Overstory. At Overstory, we combine satellite data and machine learning to better understand the vegetation of our planet, especially on and around the right-of-way. And together with me here is Indra, my co-founder. He has a technical background. His background is in business mathematics and informatics. And he will be joining me in the Q&A session. During this session and this presentation, we will take you through a couple of topics. First of all, the role of data in vegetation management. We'll discuss and dive into a couple of trends in satellite data and artificial intelligence, and also how these trends and developments evolve and what their role is in helping to identify risks in and around the right-of-way. So if we start with vegetation management, as we know, this is key for mitigating risks. Especially on power outages, safety for compliance, and of course, wildfire risks are key to mitigate, and vegetation management has an important role in this. To make sure that we better understand the vegetation in the right-of-way, we need to get the right data. So a complete view of the information and of vegetation on and around the right-of-way is needed. And we need to understand where is current encroachment. So what are the highest priority areas of the grid that have encroachment by trees? But not only where these risks are now, but also how these risks evolve and what we expect the risks to be, for example, in 6 months or even 2 years. And this is important not only for the full grid, like a full overview, but also having that granularity on tree level becomes more important. So data is key in vegetation management. And it's also a quite complex process. And I think Joe also already just mentioned there are a lot of different sources available. And what we see with our customers is also there's a large emphasis on improving these processes. What we see is that currently there are different sources of data available in different parts of the organizations and different formats. And the data structuring and centralization of these data sources really help to also extract the right insights and get as much value out of these insights, out of the data as possible. And the next step, what happens with these insights, of course, informing vegetation management planning, trimming cycles, prioritization, what area needs attention now and what areas need attention the next year or the year after. And all of this, of course, comes together in a workflow and reporting to make sure that the vegetation management workflow of trimming cycles is followed correctly, and it's possible to report and verify what's actually happening on the ground. So we see this is becoming more important and also increasingly important due to climate change. Weather events are becoming more severe and also are becoming in longer duration, for example, periods of droughts, but also extreme storms. And this is, of course, putting vegetation management, extra emphasis on vegetation management. So there are different sources that are currently used by electric utilities. And I will go through a couple of sources, and I think good to mention is they are complementary, or they can be used very complementary, and all have their strengths and their weaknesses, or their strengths and their limitations. And there's no one size fits all. So what we see is that visual inspection, especially in distribution, is still very common. The benefit of visual inspection by either walking or by driving a truck is that no deep knowledge of remote sensing is needed. However, the disadvantage is, of course, that it's possible to cover only limited areas. And our customers, for example, are dealing with some difficult terrains, very remote areas. And then visual inspection is limited in terms of scalability. Another typical way of gathering data is by helicopter, for example, with LiDAR sensors, LiDAR scanners. It has advantages, what we see especially in the level of detail in terms of height and in terms of proximity of the trees to the power line. And on the other hand, it's also costly. So that means that scans typically happen not very frequent, which means that companies are dealing often with information that's, for example, a year old or even older than 1 year. So there has its disadvantages as well in terms of scalability and cost. We see more utilities experimenting with drone images and drone flights. I think it has also, in terms of cost efficiency, some advantages over LiDAR by helicopter, but LiDAR by drones or optical imagers by drones can be a bit more cost efficient. But still the limitations in scalability are there if we're talking about tens of thousands or hundreds of thousands of kilometers of lines on a regular basis. And I will focus today mostly on satellite data and satellite imagery as a source of data to inform vegetation management. The advantages here is that it's highly scalable and cost efficient. So it's possible to scan the entire grid every single day. It's also fully remote, which is convenient, of course. While the level of detail is not there yet with, for example, compared to LiDAR, the satellite images are extremely scalable, and the real value is also in the frequency of updates. And the different layers that allow us to extract a lot of valuable insights from that. And we'd love to go into detail on that. And this field of satellite data is evolving very fast, which is allowing and also reshaping what's happening now in vegetation management. One of the factors that is influencing the world of satellite data is what we see here on the slide. It's the very fast decrease of costs of launching a satellite and launching a satellite into space. So where the costs has been at $100,000 per kilogram, it has now come down to $1,000 per kilogram. And this is expected to go down in the coming years. Up to at the end of the century, we expect only a couple of cents per kilogram. So this is an amazing, fast and rapid growing industry. And of course, we've also seen the success of SpaceX very recently. It's also had a role in this. So what is the effect of these decreasing costs on the satellite data market? It is very large. So what is happening is that there are a lot of satellite data providers popping up everywhere, in all over the world actually, and where there used to be only a couple of very large organizations building satellite satellites and launching them. There are now many different companies all around the world building satellites and bringing them into orbit. And what this means is that the amount of satellites that are expected to launch and to be in orbit in 2028 is 8,500 that are continually giving us data about what is happening on the Earth. So what is happening with this technology and these steps that are taken in the industry? So the number of satellites has increased massively, which means there is very high resolution imagery available for every point on the Earth on a daily basis. And this is growing fast. But it's not only about the number of satellites and the frequency of updates that is possible, it's also the sensor diversity that is growing. So as we know, all optical satellite data is of course an image of the Earth, but there are other sensors as well, and other sensors are being frequently launched, and the resolution is changing a lot. For example, radar data that helps us to look through clouds, but also hyperspectral data, which gives amazingly rich and nuanced information about vegetation. For example, to better understand vegetation health or tree species, this is extremely relevant information that is becoming available global at this moment. A third pillar here, what is changing, and that we're now not only looking at single images of the Earth, but stereo and video are becoming way more frequent. And this means that we can extract 3D maps of what is happening on Earth. So 3D maps of the right-of-way. And for this, we combine different images from different angles to extract that height map and that 3D mapping of the planet. So these many petabytes of data that are available of our Earth all the time are of course only valuable when we can extract actionable data from them, and for utilities and organizations to extract, to link it to a specific action that will help improve their business and the planet and the goals we try to achieve. So with many new sources of data, it is also important to look at what are the new sources and the new developments to automatically and efficiently extract the insights and the actionable insights we want from those large amounts of data. And this is where artificial intelligence plays a role. There are large developments in artificial intelligence, and what we have seen for Earth observation is that, especially in deep learning, there have been major increases in accuracy, and the adding of deep learning to Earth observation has granted a lot of success for analyzing satellite imagery and better understanding vegetation around the right-of-way. Where before algorithms, more, let's say, traditional machine learning algorithms, including random forests, were used that really focus on what is happening on a pixel, and looking at each value of the pixel. Now we see that convolutional neural networks are being implemented, and that means we don't only look at pixels, but we look also at the context of the pixel. So, for example, this is relevant when we want to understand a tree species. This has a shape and it has a structure and it has a pixel combination that is relevant to identify the species. So that is where neural networks and convolutional neural networks are highly important. But like every technology and every method of analyzing, also deep learning has advantages and disadvantages. So advantages of deep learning for Earth observation are, as I just already mentioned shortly, it is possible to understand structures and to understand patterns. So it's possible to extract complex patterns, such as tree species, but also, for example, patterns over time, such as disease patterns. Next to that, it is possible to have the models can be very generalizable. So it means it does not only work for one part of the planet or one part of the country, but it also generalizes. The same model can be applied to different parts of the planet while keeping its performance. There are also disadvantages. One disadvantage is that the models are very data hungry. So there is a need for very high quality and high quantity ground measurements for training and validation. And this is especially the case for when we look at vegetation, when we look at forests and trees. This is even more the case than for like other tasks, such as identifying cars, for example, where a car is more straightforward. A tree and forests and vegetation look different in different seasons. They look different in their different growth stages, depending on the terrain, depending on the geographical area and climate region. So this is why, especially for vegetation, very high amounts of training data are needed to get the most out of using deep learning for Earth observation. So, of course, we also use deep learning for computer vision or for Earth observation. And how we deal with this is we have invested, as Overstory, we have invested in large amounts of training data, both in Europe and the US. So I think our data repository stems from our work with forest industry companies, for example, that have, of course, in nature access to a lot of data on forests. So we partner with them and also with NGOs, for example. And these forest data assets are a huge asset to our algorithms, and also, of course, also to the utility customers that we work with, especially because they typically don't have that knowledge and data in-house. So the added value, so the combination of satellite data and artificial intelligence has added value for vegetation management. And we see that in three parts. First of all, the frequency of updates and the speed of which we can scan an area. Secondly, planning ahead due to predictive insights. And thirdly, tracking and verifying, also due to the frequency of updates. It's possible to track what is actually happening and verify and report on that. And to illustrate this a bit more, I will share different examples of how we do that with Overstory, and I'll explain the steps on that. So the first step we take into account in this application for utilities is creating a base map. And this is, for this we use stereo data. So we take images from different angles and we extract a map of the current vegetation around the transmission and distribution network. This gives a view of current encroachments, and it gives a view of proximity of trees to the line or to the pole, as well as the height of the tree extracted. And you see that in this picture with the color visualization, but every pixel has a value, of course. The beauty of satellite data here is that this can be done every single day for all parts of the grid. But we're not only looking at the current encroachment, because to get a better understanding of current risk, but also future risks, we also look at grow-in risks. And for this, we especially look at tree species. And for that, we use a combination of multispectral and hyperspectral data to better understand what are the different tree species growing in the right-of-way, or around the right-of-way, of course. The reason why this is valuable for our customers is twofold. The one is, when knowing the tree species, we also know the growth rate. So it informs whether the tree is gonna, how many meters or how many feet the tree is gonna grow in the next year, next 6 months, and next couple of years. So it really informs growth risks or grow-in risks, and it helps to plan ahead. The second point is for customers in Europe, mostly understanding the tree species, especially in the transmission corridor or around the transmission corridor, is needed for compliance. Some tree species should not be in the right of way due to they're, for example, very fast growing, this needs to be monitored and it needs to be taken care of regularly. So this is why compliance is also one of the reasons we monitor tree species, for example, in Southern Europe. So currently the risk profile includes current encroachments and grow-in risks, but to inform vegetation and trimming cycles even better, we also look at fall-in risks. How we do that, or how we approach this, is by looking at the vitality of trees. For example, what we see here in the picture is bark beetle attack. Why is it important to look at the vitality of trees? When a tree has very low vitality, it has the risk of falling down, especially when there hits a storm. So any low vitality trees close to the line or in the border zone, for example, are a risk. But we typically not only scan the right-of-way and the border zone, but we also scan a broader area. And the reason for this is when there's a bark beetle attack, there's a risk of spreading, of course. And typically this, if the tree is not removed, this bark beetle infestation spreads. So by understanding a bit broader area, we can also help mitigate the spreading towards the right-of-way. So a risk profile combining the current encroachment risks, the grow-in risk, and the fall-in risks are relevant. But these are preventive ways to inform trimming cycles. We also, the technology of satellite data and artificial intelligence also helps in verification. So verification of trimming, for example. Was the work order performed by the contractor, or was it executed by the contractor? Yes or no? And this technology really helps to verify whether this has happened, yes or no. For example, here we see trees being removed near distribution poles, or actually trimming of the canopy has happened. And a last element of the benefits of this technology has less to do with preventive or verifying. It is really about the actual damage. So storm damage in this case. So the red dots we see, or the red stars we see here, are actually storm damages. And this is a beta test we're currently running, and the goal is to scan immediately when a storm hits. So instead of really to inform as soon as possible after the storm has hit, what has happened, where the damage was, and what the likely location and impact has been. The type of data we use for this is radar data. We see this works best for storm damages, especially because radar data, or when it's stormy, it's often very cloudy. So we need to go through clouds. And with optical data, this is of course limited for clouds when it's very cloudy. Actions. So I've shared a couple of examples of how this technology works and how it's possible to combine satellite data and machine learning to understand the vegetation around the right-of-way, or in a broader sense, threats of vegetation. But what really makes it actionable is when it is visualized in the right way, and it is shared with the right stakeholders at the right time in the right way. How we approach this typically is our platform allows to connect with the workflow of trimmers. So we prioritize based on the detailed insights on tree level. We also prioritize what are the risks per segment and what is the risk level of each segment. And next to that, there's a view for managers that better want to understand more on an overall view of the grid. What is the risk level and how is this changing? And what is the effectiveness of my vegetation management actions and strategy? To conclude, what we see is that vegetation management is becoming more important and also more data-driven, and climate events, extreme climate events such as severe drought or storms are also asking more from vegetation managers and from the vegetation management function in general. Where we see what the technology of satellite data and machine learning typically offers and also develops is 3 layers of, or 3 steps of information. The first and most basic step is perceiving. So what do we observe? What is actually happening? Where are trees encroaching right now? And what's the current height and distance? The second layer of information is predict. So what are the risks and also what is their potential impact, including where are danger trees, where is a tree growing, so can we identify grow in and fall in risks already in a very early stage. And the third step is prescribe. So how do we act on the perceived intelligence and also on the predicted intelligence? How can we help, how can this data help to improve our trimming cycles, move to a more risk-based or risk-informed approach, have targeted maintenance, which also is more cost efficient, of course, and verify the actions and verify our vegetation management strategy. This is, of course, not possible without collaboration in the industry. So we see utilities working together, collaborating with environmental research, with research in the energy sector, as well as with regulators. And this is, I think, also key to make sure that these steps, both the perceive, the predict, and especially the prescribe, is done in the right way. At Overstory, we want to bring in, and we aim to bring in our expertise to this conversation and to this table. We combine very high resolution satellite data and machine learning to create data-driven and actionable vegetation intelligence, especially for better understanding of vegetation in the right-of-way. Our customers are from different industries. We've worked with forest industry companies, for example, such as global leaders such as Stora Enso, and also with NGOs such as Rainforest Alliance. And these partnerships also really fuel our application for electric utilities. And I think this has been a very strong asset we have helped bring in to bring in this expertise on not only satellite data and artificial intelligence, but also really on the vegetation management aspect. We partner with partners including Planet, Maxar, and Airbus. They're providers of high-resolution satellite data. And our investors include Techstars, Pale Blue Dot, and Powerhouse. We are very eager to be here at this event, and we'd love to communicate with you also afterwards. So if you have ideas on collaboration, or if you think we could potentially partner, on this topic, or if you're interested to learn more, feel free to reach out and feel welcome to reach out. And of course, my colleague Indra and I will also be part of the Q&A session. But for now, I want to thank you for listening, and hope to speak with you after this event also.
Thank you, Anniek. Very interesting talk. Really gives a lot of ideas on questions that could come about that I have come up with, but I have the first of our questions from our attendees. Tristan asks, does the platform utilize utility provided right away and facility mapping to determine the risk, or is it a function of relative positions of wire location to the vegetation as determined from the stereo imagery? Does that make sense to you?
Yes, but before I answer, I would like to bring on Indra, my colleague, as well. You can help there as well. Maybe I already introduced you shortly, Indra.
Yeah, I think to answer the question, I think depends on what the utility has in-house themselves and what the accuracy is of the data they have themselves. We prefer to extract this information from the satellite imagery ourselves, as you mentioned, also to get the relative position. So then you have the relative position of the wire versus the vegetation directly in the same image. But yeah, I think it depends a bit on case by case, what is available from the customer, what can they share, and what can we extract from the imagery itself, because not every power line can be extracted, especially if you look at distribution from the imagery. So often it's a combination of the two.
Thank you. So one of the things that intrigues me is that I know from using optical images, people have been able to draw conclusions about vegetation health, especially looking at the near-infrared or the entire infrared spectrum. But you implied that you're using multispectral and hyperspectral data, which I'm assuming comes from satellites. Is this able to give you a much, let's call it a finer gradation or fineness of evaluation compared to infrared? Is that why multispectral and hyperspectral figures in your technology?
Yeah, I think near infrared is one of the bands, and I think the beauty of satellite imagery is that we have many more bands and that we have multiple images over time. So I think definitely there's some added value there to have also the other bands. And I think it also this depends on the case by case basis, like what is the mixture of the forest, what kind of canopies are overhanging other trees. But in general, the multispectral has been very valuable for us, and I think we see now also an increase of satellite-based hyperspectral data, which will be more interesting as well for tree health, for example, moving forward. But it's not available at scale yet, but it's an interesting direction where the market is moving as well.
And maybe as an addition, so we've worked in forestry also quite a lot. And of course, they have the issue of unhealthy trees or bark beetle infestations quite heavily. So they have also quite large, some have quite large historical data sets on this. And we typically use this historical data set also to better understand what is the pattern of this disease evolving. And by training the algorithm also to understand the pattern, we try to detect the outbreak also in an earlier stage. So by using patterns, historical patterns, actually we try to recognize those patterns in an earlier stage now by using indeed these data sources.
So the next question comes from Thomas, and this might mean that you have to go back to your university education to answer this one, but can you define multispectral compared to hyperspectral?
Yeah, so in the satellite space, how we compare those two. So multispectral is fixed number of bands often. So we have Sentinel-2 images that is 12 bands, for example. Most very high resolution have 4 bands, RGB plus near infrared. But for hyperspectral, we actually have a continuous reflection of the surface. So then we have, in theory, you can have an unlimited number of bands, but often it's tens or hundreds of them. And of course, then you can see small differences in the reflectance of the tree canopy. And then it's easier to also distinguish between different types of pine tree, for example. So it's very, very valuable. It's, as I said, it's not globally available every day yet, but it's becoming. And that's, I think, a very interesting direction.
So I think you have Thomas's attention because he's already asked a different question. Doesn't sound like power lines, but since you guys are the experts so far who've spoken at this conference on this subject, I'm going to go ahead and ask this. Can this technology, meaning either hyperspectral or multispectral, can also be used for underwater plant identification like seaweed or milfoil in salt or freshwater environments? Do you have any experience with that?
No, I wouldn't call this our expertise, but I know I know there's some research in this field as well. So I'm also curious what the answer is to this question, but unfortunately I cannot answer it myself.
Very good. So my guess is that in shallow water, as long as it's relatively clear, that probably the answer is yes, from having attended other conferences involving not necessarily satellite data, but certainly even drone data that collects multispectral or hyperspectral data. I know there's been a lot of bathymetric work done just to detect where the bottom of the seafloor is in shallow waters, but I think as part of that, they accidentally discovered that they could do a lot of analysis of the vegetation in the water as well. So that's an informal, that's not an expert answering, it's what I've heard at other conferences, so definitely don't take that one to the bank. I was very intrigued by your bark beetle story. So to me, and I'm not a forester, but I think bark beetles are normally things that are probably detected only after the damage is done, unless you have entomologists and forest experts who can really gauge the health of a forest by visually inspecting, meaning walking through the right-of-way. So I think what you're suggesting here is that it's possible to detect bark beetle activity without doing that. Is that correct?
Yeah, I think it depends in what stage it is. So I think even if you walk in the forest and you're an expert, then it's sometimes also in early stage is still not possible. You have to go really close, look at the bark of the tree. But I think it's also only possible to see it after 1 or 2 weeks. And the idea with satellite imagery is, can you detect it at an early enough stage to prevent further spreading? So of course, after a year, you can see it. It's clear, there's decolorization. It's very clear with the naked eye, but what we try to do with the hyper and multiple spectral data is to try to detect it in an earlier stage. So between 4 to 6 weeks after infestation, when there's still a chance of spreading further. And that is actually what we're trying to limit. So there's, of course, now it's actually actively happening here in Northern Europe as well. We want to detect that during the summer so that we can prevent future outbreaks as well. And remove the trees that can lead to new infestations. So it's definitely only detecting after the event has happened, but we can still have an impact by removing those trees early on, preventing them from spreading further. So that is what we are looking for, making sure we can detect it. And I think the beauty of satellite imagery is that we do entire countries for this as well, and we can do that every day. And I think that helps also the people on the ground to go to the right location and do further field work.
And this is a topic, this is a topic that's also growing because of like warmer temperatures. It's also easier for the bugs to survive and swarm. So it is a topic that is also becoming more important, and also in regions that had not that didn't have that problem before.
So have you participated, or do you have knowledge of case studies where you compare some of the technology you bring to bear, hopefully to do things faster, with a quicker, giving people a quicker response time, compared to the traditional methods? Is there any history of case studies here that you can talk about the economic impact of the kind of work you're able to do?
Yeah. We work with different clients, mostly in Europe, and now we're expanding to the US. And what we see now is that it is mostly used in combination, at this moment at least, in combination to other existing technologies. For example, to better target or plan LiDAR scans, for example. So I think this is the first step of adoption of this technology. And I think that is one element of it. And the second element is the economic, let's say, changes with regards to trimming cycles. So instead of having a fixed trimming cycle, in place that is only time bound, by really understanding what are the risk areas, we are looking to let's say, have more insights to do that more risk-based. And we're currently testing this out also with clients, and hopefully we can share those results also very soon. But we can talk more into detail, but then after the conference, if that's okay.
Very good, thank you. So Tristan asks a very important question: are there integration options for the Overstory products with existing GIS software, or is it generally a standalone tool?
Yeah, I can take that one. I think half of our customers connect via our API, and other half use our tool as a standalone tool. So we know that most of our customers have their own platforms or other standardized platforms that they use. We have built an API to connect with some of them. Some need some customization, but we do integrate with other tools just by providing a simple API to connect and extract this data from our servers.
Very good, thank you. So I was intrigued by your use of radar. I don't think you actually talked about which radar, because obviously there's many ways to use radar, and the actual transmission of the radar signal itself can be done in so many different ways, and the analysis can be done in so many ways. So you mentioned that it's particularly good for storm damage, and that's because you have cloud cover. That's an obvious reason. You cannot do any, it's difficult to do optical observation right after a storm, and you still have the cloud cover. But how are you able, and is this satellite-based or is it aircraft-based radar, and what kind of radar, and what's the analysis technique that's used to detect fallen trees with that much resolution?
Yes, so we're also talking about satellite-based radar here. So combination of public radar like Sentinel-1, which is C-band sensors. But we also complement it with higher resolution satellite-based radar. So you have TerraSAR X, for example, which is X-band radar and has resolution up to, I think, 25 centimeters, the highest they can get. So we use that, and I think specifically for this storm damage, after the fact, we try to task as fast as possible a high resolution scan to detect these smaller changes. And we're really looking at a different signal back than before. So we always need a before and after sort of baseline to see what has changed, where were trees standing and where has these trees fallen down. So I think now in the phase we're mostly looking at larger storm damages areas that can have impact on the power lines or on the forest in general. But we're very much developing that as well to see what is the smallest change that we can detect with radar, I think it's a bit especially satellite-based radar is a bit underappreciated still, but it's also complexer to handle, of course. So that's currently we try to combine them both and fuse optical with radar as much as possible as we can. But in certain situations, we cannot depend on optical because of the clouds, and then we use the radar. But preferably we combine those two.
So just a quick question before we switch over to the next speakers. How accurate are your algorithms? You know, you're using software, whether it's artificial intelligence, machine learning, or deep learning. You're asking people to put a lot of trust in the ability of the software to detect whatever it is that you're trying to detect. So how do you validate it? How accurate is it?
Shall I take this one, Indra? Yeah. So validation is for us key. So what we always do with every single client is having them independently validate our models, the output on the ground. And the reason for that is that it's not only allows us to really understand what the accuracy of the output is in that specific region, but it also gives that trust, like, all right, this is, I've seen this with my own eyes. So we put a heavy emphasis on both cross-validation and blind validation here. The accuracy really depends on the feature we're trying to, we're launching, or a feature we're implementing. For example, for tree species in Southern Europe, we have achieved accuracies, we look at precision and recall. So we look at F1 score typically, and we've had accuracies up to between usually 90 and 95%, but it depends on the number of classes we're trying to implement. So for this result, we have, for example, implemented 5 different classes, but we're also looking at now extending that to 30 different tree species. And that means also it has, of course, impact on the result. But that is why validation and on-the-ground cross-validation is key for our process. And that's also how we can communicate very openly about how our algorithms are performing on that specific piece of land and that specific region. Any additions to that, Indra?
Very good. Well, thank you both, Anniek and Indra from Overstory. It's time to move on to the next speaker. So